Hi, if you're watching this video, you're watching the second video in optics. In this video, we'll be talking about reflections. So in light and optics, a reflection is when light strikes an object and bounces back, right? Now, it's important to note that it's when light strikes an object and bounces back and creates an image, right? Because if light is reflected off a very smooth surface, it will create an image, a reflection. So a reflection is when light strikes off an object and bounces back. If light is reflected off a very smooth surface, it'll create an image. So when we look at this picture, and this person's looking at their eye, light is striking the mirror and then bouncing off and entering our eye. And we'll be talking about how the eye works in a future lesson. So light will strike the mirror. Now the mirror is very smooth, right? You very rarely, if ever, see a rough mirror. And so light will bounce off that mirror into your eye, and that's what creates that reflected image. So when light is reflected on a smooth surface, it bounces evenly along the surface. So if the surface is smooth, like we see in this picture, right, light is going to bounce evenly, meaning that, one sec, if this is reflecting at like a 45-degree angle, all the light reflections will bounce at a 45-degree angle. So in this ray diagram, remember a ray diagram is a diagram that shows rays of light. In this ray diagram, we see that light is hitting here and bouncing up, but so are all the other rays. All the rays are hitting at the same angle, right? So if this light ray is hitting at a 45-degree angle, so is every other light ray. And so the reflections on a smooth surface will bounce in the same direction. But when we look at this picture, rough surfaces cause light to bounce at different angles. So even though all these rays, these green rays, are all hitting at the same angle, they're hitting different rough edges. And these rough edges cause the reflections to bounce in different angles. And so because it isn't this evenly distributed light that's bouncing off, you don't create this image that you'd see in a mirror. So most things have a rough surface, which is why everything isn't a mirror. So when you look at something and you don't see your reflection, that means the surface light is bouncing off of isn't smooth enough to create that smooth, nice transition of reflection, right? So, angles that light strike. When a ray strikes a surface, we call that ray the incident ray, right? So in this ray diagram, you can see the ray here is hitting the mirror. So this is our mirror, right? This ray is hitting the mirror, and this is coming from the source, be it the sun or a flashlight, right? And we call that the incident ray. The incident ray is the ray that is creating the source of light, right? So the rays coming from the source, we call that the incident ray. When the ray is reflected from the surface, we call that the reflected ray, right? So this ray is coming off the surface, so it's the reflected ray. This is coming from the source, incident ray. This is coming off the surface, the reflected ray, right? And so you may also see angle of incidence and angle of reflection, and we'll be talking about that in just a moment. So in between the incident ray and the reflected ray, we draw a dotted line. We draw a dotted line. And now this dotted line here is called the normal. In later units in math, you will know what a normal means, but for this unit, we'll just call this line that cuts the reflected ray, right, the reflection point, in half. We call that the normal. The angle of incident is the angle of the ray to the normal. So let me just use a different color. So if I were to use, let's say, purple, this angle here is the angle of incident to the normal. So we call that the angle of incidence. And the angle of reflection is the normal to the ray. And we call that the angle of reflection. The angle from the incident ray to the normal is the angle of incidence. The angle from the reflected ray to the normal is the angle of reflection. So the normal is important in finding out the angle of incidence and the angle of reflection. Now maybe asking, why is it important to know the angles of light? But again, it's important to know this to know how light is moving, how light travels, where shadows are going to form, and what's going to block or change the direction of light, and by how much. So it's important to know the angles of light and where they're coming from. The angle of incidence, so this original angle here, is always equal to the angle of reflection. It's always equal to the angle of reflection. This is called the law of reflection. So if you know the angle of incidence, you automatically know the angle of reflection. The angle of incidence and the angle of reflection are always the same. And this is called the law of reflection. So if I said, what is the law of reflection? You would say the angle of incidence is equal to the angle of reflection. So let's take a look at this practice set of questions. What is the angle of reflection? So what is the angle from the normal to the reflected ray? Well, if we go back, the angle of incidence is always equal to the angle of reflection. Well, this is the angle of incidence, right? Incident ray, normal. So the angle of incident is here to here, so that's 45. So what should this be? Well, hopefully you came to the conclusion that this should be 45, because the law of reflection states that the angle of incidence must equal the angle of reflection. So let's change it up a bit. In this case, I have this angle. I have 35 degrees over here. What should the angle be here? So pause the video and figure that one out. Okay, hopefully you paused it. So we know that this is 35 degrees. Well, this can't be 35 degrees, and that would be a common mistake some people would make. They would say that this is 35. Well, no, this is not 35. Why? Because this is not the angle of incidence. This is. That's the angle of incidence. Okay, well then how do I find this guy? Well, if I know that this is 35, and this is the surface, well, the angle from the surface to the normal, well, that looks like a right angle, right? Well, if the normal creates a right angle from the surface, like so if you draw this and then draw that, then we know that this whole thing must add up to 90 degrees, right? So if I have 35 degrees on this side, then my normal should be 90 degrees, right? 90 degrees minus 35. Because the left, both of these angles need to add up to 90 degrees, right? So 90 degrees minus 35 would be 55. So this is 55, 55 plus 35 is 90, perfect. So the angle of incidence, should be 55. Well, according to the law of reflection, the angle of incidence must equal the angle of reflection. So this must also be 55. Did I say 35? I meant 55. So you can see how you can change these styles of questions up to be a little bit trickier. But remember, if you find out what either the reflected ray is or the incident ray is, then you know what the other one is naturally, because they have to be the same according to the law of reflection. So let's do this question. So pause the video and see if you can solve this one. Okay, so in this situation, we have 50 degrees here to our normal. Well, if this is our normal, right, that means that this side must equal this side. It doesn't matter if this is the reflected ray or not. because they both must be equal. So this must be 50. Okay. Well, if this is 50, then what is this? Right? What is that missing angle? So when we look at this angle is the same. And the reason why it's the same is because if you look at it this way, this line is hitting the same angle. Right? This line is hitting at the same angle. So this one must also be 50. Well, if this is 50, remember this is a right angle, this must be 40. Well, according to the law of reflection, the opposite side must also be 40. Well, then this must be 50. Now, why is this 50? Is because these opposite angles must be the same. So this is 50. Again, according to the law of reflection, this must also be 50. And so you can make challenging questions like this just by using the law of reflection and by repeating this rule. So it's important to understand what the law of reflection is and how angles work. You must also understand right angles, right? Just like in math with Pythagorean theorem. Understanding that this normal creates a right angle with the surface, well then you know whatever this is plus this must be 90. And so you can fill in the blank and say that that is 55. It's relatively easy to find normal lines on smooth surfaces, right? When these are bouncing off of smooth surfaces, they make nice, neat angles. But what about rough ones? Right? When we look at a regular reflection, it goes down, up, in the same way every time. And they all look the same. But when we're looking at this picture, we see lines doing this, lines doing that, and lines doing this. And they're bouncing all in different directions. How do we find the normal and the angle of reflection on rough surfaces or ray diagrams that are reflecting off of rough surfaces? Well, to find the normal of a rough surface, you need to draw a straight line that evenly divides the incident ray and reflecting ray, right? So if you were to draw a line directly down the middle here, you've now created a normal. Here, the normal would come in like that, because that evens out the line. It's not the best line because the line's thick. There, right? And there. And so all of these would be normals because they divide the angle of incidence to the angle of reflection evenly. When looking at a reflection, the image in it seems as far away as the mirror as you are. So if you were standing 2 meters away from a mirror, your reflection in the mirror would also look like it's standing 2 meters away. And that seems like common sense, right? If you're standing 2 meters away, your reflection looks like it's standing 2 meters away. Now, it's not actually, right? You're not going to walk 4 meters to meet your reflection. But it looks like it's roughly 4 meters away because 2 meters from the mirror and then 2 meters in the reflection. Curved mirrors. Well, when you take a smooth mirror and bend it, you can also alter the reflection. So in a normal mirror, the object or person you're looking at looks the same and looks about the same distance away. Well, if you take a curved mirror, you can change the image. Concave mirrors bend light inwards, right? And it's called a concave because it bends inwards. A good way to remember it is it kind of bends inward like the entrance to a cave. And then we have convex. I like to think of convex as flex because it kind of looks like a muscle flexing, right? It bends outwards. This is important because a common mistake that students make is they confuse their concave and convex mirrors. Concave mirrors bend inwards, and convex mirrors bend outwards. And they do different things to the reflection of light. So a concave mirror will focus light towards the center, right? It focuses light towards the center. So this allows light to be focused on one spot. In addition, these mirrors also reverse or flip the image being reflected. For example, if I were to take a person, like so, and have the light that's bouncing off him hit the mirror, well, this is the light coming from the head, right? Or light, let me just use a different color. This is light reflecting off his head. Sorry, it's not straight. Hits the mirror and comes down that way. So if I keep drawing the line here, oh, we have the head over here, right? If I draw from, I guess, his body, from here, and it bounces there, oh, his body's over here. If I take from the middle part and bounce it here, we have his legs over here. So you can see how this would create an upside down image, right? The light from the top hits the top of the mirror, but ends up downwards. So concave mirrors focus the light, but they also flip it. They flip the image you see. So you will look upside down in a concave mirror. A convex mirror is a mirror that scatters light. It spreads the light out. It also makes the image look smaller. Right? So when you look at a convex mirror, the light ray will strike it and then bounce off and away. The light ray will bounce off and away. And so it scatters the light. In this one, it focuses the light. And so when something is focusing the light, the image is going to look magnified. So concave mirrors not only flip the image, but magnify it. Convex mirrors do the opposite. They shrink the image and scatter the light. So, concave, focus light. Convex, scatter light. Because curved mirrors cause the light to bounce at different angles, the image formed is also different. You're not going to get a nice mirror. We call the image created by these types of mirrors a virtual image because they're not actual accurate representations of what's being seen, right? If you stand in front of a concave mirror, you'll look upside down and closer to the mirror than you actually are, right? So we call that a virtual image. If you were looking into a convex mirror, you would look like you were standing much further away and you would look much smaller. So again, because they change the actual image, we call it a virtual image. So just as a quick review, try and fill in the blanks for each of these arrows. So pause the video, see if you can figure out what each of these terms are because they will appear on a quiz. Okay, hopefully you paused it. So this ray here, pointing to this is called the incident ray, right? Or the ray of incidence. Either way works, right? This ray here, because a ray is a straight line with an arrow to describe light, is called the reflected, right? Reflected ray, right? Well, if this is the incident ray, and we're looking at this angle, this is the angle of incidence, right? The angle of incidence is this. And this must be the angle of reflection. And so it's important to know these key features because I'll show you a ray diagram and ask you to label the key arrows. So one last question to think about. Why would a side view mirror say objects look closer than they appear? Or, sorry, not look closer, are closer than they appear. I should change that. So why do side view mirrors say objects are closer than they appear? Why would a side view mirror say objects are closer than they appear? So think about that as we end off this lesson. Hopefully this was helpful, and I'll see you next lesson.